It was early morning, February 22nd, and I was standing outside in Cincinnati in that strange window of time when the night hasn't quite decided to leave yet. The cold had a specific texture to it, not the biting kind, more like a pressure, something leaning on you from everywhere at once, the kind of cold that makes you stand still instead of moving through it. I was looking up, not for any particular reason, just up. The sky was doing that thing it does in late winter, where the stars are sharper than they should be. Drier air, maybe, less in the way. And I remember thinking, I wonder which of these are still there, not in a dramatic sense, not with any urgency, just a passing thought, the kind that arrives and floats for a second before the mind moves on to something else. The coffee getting cold on the counter inside, the way my fingers had gone numb without my noticing. But the thought stayed. Which ones exactly am I looking at right now that are still producing light? And which ones are images, leftovers, old photographs developed across 2,000 years of travel, of something that ended before I was born, before anyone alive was born, before the word star existed in any language? That's already a lot, just standing there before we get to any of this. Somewhere, and I mean this literally, not metaphorically, there is an archive, a physical building with shelves and controlled temperature and the particular silence of rooms that are meant to preserve things. Inside it, among other objects, there are glass plates, large, heavy, coated in a thin emulsion of silver halide crystals. Not film in the modern sense, actual glass, the kind of thing you'd be nervous to carry. These plates were exposed at Palomar Observatory in California. The date on the ones that matter most here, April 12, 1950. Someone loaded the plate into the telescope housing that night, set the exposure, waited. The shutter, or whatever mechanism served as a shutter then, opened, and light from an enormous slice of sky fell onto the glass. Photons that had been travelling for years, decades, centuries hit silver halide crystals and caused a chemical reaction. The crystals darkened, a record was made, then the plate was removed, developed, catalogued, given a number, filed. The person who did this probably went home and slept. What's on those plates when you look at them now, and researchers have, very carefully, digitized and examined them, is a picture of the sky as it was, not as it is, as it was, 70-odd years ago. And that distinction, which sounds small, turns out to be the whole problem. Because when you compare what's on those plates to what the sky looks like today, most of it matches. Stars in the same positions, same relative brightness, same patterns. The sky is mostly stable on human timescales. A constellation you recognise tonight would have been recognisable to someone standing in the same spot in 1950 looking up, maybe also with cold hands. Most of it matches, not all of it. There are points of light on those old plates, specific, catalogued, numbered points of light that are simply not in the sky anymore, not dimmed, not moved, not exploded into something recognisable, just absent. The coordinates are empty. You point a modern telescope at where they were, and there's nothing, or nothing detectable, which, given how sensitive the instruments are now, is more or less the same thing. I keep coming back to what that actually means, and I'm not sure I've fully landed on it yet. A photograph is a record of light. That's the simple version. You open the shutter, light falls on a surface sensitive to light, a reaction occurs, and you have preserved, in some physical form, the fact that light was present at a particular place and time. The silver halide crystals on those Palomar plates don't know what they recorded. They don't know if they captured a star that still exists or one that doesn't. They just darkened where the photons landed. The record is neutral. It doesn't grieve. It doesn't mark certain stars with any special notation, but we can look at it now and notice the absence. We can hold the old image next to the new one and find the gap. There's something strange about that process. Not philosophically strange, just genuinely strange. The plate is more permanent than the thing it recorded. The image outlasted the source, the glass still exists, the star doesn't. Or it exists in a form we can no longer see, which may be its own kind of not existing for all practical purposes. Standing outside in Cincinnati that morning, I wasn't thinking about any of this directly. I was just cold, looking up, vaguely awake. But something about that moment, the sharpness of the stars, the specific weight of February air, the sense of seeing things that were also somehow seeing me back, felt like the right way into this. Because here's the thing that doesn't quite leave me. Someone else stood somewhere, looking at roughly the same sky, maybe not Cincinnati, maybe California, maybe Spain, and recorded it, carefully, with glass and silver and long exposures, and what they captured included stars that no longer send us any light at all. They didn't know that's what they were doing, they were just looking, recording, moving on, and we are the ones who noticed the absence, later, decades later. By comparing the past to the present and finding the places where the two images don't agree. That's what this whole thing is, at its core. A comparison, a difference between then and now, a gap that nobody made. It was just there, waiting to be found. I went back inside, made the coffee, warmed my hands on the mug. But the sky stayed with me, the way it sometimes does. Not urgently, just present, sitting at the edge of the morning like something that had wanted to say something and hadn't quite found the moment. The glass plates are still in the archive, still holding the light from that April night in 1950, still carrying in their silver-darkened surfaces the image of stars that were there then and are not there now, and that distinction, which the plate itself cannot feel, is the thing we're going to sit with for a while. There are other things to say, about what the stars should have done when they ended, about what a star collapsing looks like, or more precisely, what it doesn't look like, about the specific night in 1950 when 9 of them in the same region of sky vanished within half an hour. But that can wait. The plate sits in its archive. The stars are not there. That's enough to hold for now. The word vanish is doing a lot of work here, and I'm not sure it's the right word. Disappear is worse, somehow. Disappear implies someone watched it happen. Vanish implies what exactly? A magic trick? Something there one moment and gone the next, with an audience, with a reveal? Neither one quite fits what's actually going on with these stars, which is something quieter and more administrative than either word suggests. What happened more accurately is this. A record was made. Then decades later, someone checked the record against the present, and the present didn't match. That's it. That's the whole thing stripped down. No one watched a star go out. No alarm sounded. There was just a comparison, an old image, new image, and a column of discrepancies that kept not resolving into anything clean. So maybe vanished is shorthand, a way of pointing at the discrepancy without having to say sources present in archival photographic survey data that are absent in contemporary observation catalogues, which is accurate but takes something out of it. I get why people use the dramatic word. I've been using it too. It's just worth knowing that the drama is borrowed. There's a version of this question, what does it mean to vanish? That belongs to physics, and a version that belongs to something else, and they're not the same question even though they sound like it. The physics version is tractable. You ask what processes could remove a point source of light from a location where it previously existed. You list them. You eliminate the ones that don't fit the evidence. You work through it. The other version is harder to put down. It keeps coming back up. Think about what it means for an object to exist, in the most ordinary sense, not philosophically, just practically. A thing exists because it can be detected. It interacts with something. It emits, absorbs, reflects. A star exists, in any useful sense, because it produces light, and that light arrives somewhere. The light hits a plate, or a sensor, or a retina. A reaction occurs. A record is made. The star has announced itself. Now remove that. Not the star, just the announcement. What's left? This is where it gets genuinely uncomfortable. And I don't mean that in a performative way. I mean it took me a few days with this to realize what was bothering me. It's not the star being gone, it's the gap between gone and undetectable. Those two things are not the same, but from where we're standing, which is here, which is a planet in one arm of a galaxy, with instruments that are excellent but not infinite, they function the same way. A star that has collapsed into a black hole and a star that has drifted behind an obscuring cloud of dust are, to us, identical problems. We can't see either of them. The difference is, one of them still exists. Probably. Astronomers have an actual term for this, not vanished, something more careful. Transient. A transient source is one that changes brightness on timescales short enough to notice within a human observation window. Stars that flare, stars that pulse, stars that orbit something that periodically eclipses them. These are expected. They have mechanisms. They are interesting, but not mysterious in the way that generates a long stare at a spreadsheet at 2 a.m. The stars in question here are not really transients in the standard sense. A transient implies return, or at least the possibility of return. What the VASCO catalogue found, or started finding, the work is still happening, are sources that were present in 1950 data and absent in contemporary data, with no detected counterpart in any subsequent observation, at any wavelength. Not just visible light. Radio, infrared, X-ray, nothing. That's a stricter definition than vanished. And it's the stricter definition that makes this uncomfortable. Here's the thing about absence, though, and this is where I keep getting stuck. And I'm not sure I'm going to land this cleanly. Absence is not a thing you can observe directly. You can only observe the lack of something you expected to find. Which means the whole project of cataloguing vanished stars depends entirely on the accuracy and completeness of the original records. If a star was misidentified in 1950, catalogued as a star when it was actually a brief flare from something else, a cosmic ray artifact on the plate, a transient that happened to occur during that one exposure, then its vanishing is not the star leaving. It's the record being wrong. The VASCO team knows this. They've spent considerable effort trying to rule it out, checking plate quality, looking for known artifact signatures, cross-referencing with other catalogues from the same era. Their filtering process narrowed hundreds of thousands of initial discrepancies down to around 100 candidates that survive serious scrutiny. That's not 100 confirmed vanished stars. It's 100 cases that can't be easily explained away. But, and this is the part that stays with me, the can't be easily explained away is not the same as definitely real. It's just the boundary of current understanding, which is a meaningful thing to be at, but it's not a conclusion. There are 3 broad categories of explanation that get proposed for these disappearances, and none of them is satisfying in a tidy way. The first is instrumental or archival error. The 1950 image was wrong. The second is a known astrophysical process that we just haven't pinned down in this specific case. A variable star at an extreme phase. A supernova that faded faster than expected. Something with a known mechanism but unusual parameters. The third is something that doesn't fit existing mechanisms well, which is the category that gets scientists interested and also causes the press releases that use words like mysterious in the headline. The third category is small, genuinely small. Most of the candidates probably belong to the first two, but most probably still leaves a remainder, and remainders are what research lives in. What the remainder is pointing at, possibly cautiously with all the appropriate hedging, is that some massive stars may end in a way that produces no visible trace, no supernova, no neutron star, no glowing shell of ejected material expanding slowly through the surrounding gas. Just the star, and then not the star. A direct collapse into a black hole so complete that nothing escapes to tell us about it. This is considered possible. It has theoretical support. It hasn't been confirmed cleanly in any specific observed case. The VASCO stars are at this point candidates for that process, not confirmed examples of it. That's an important distinction, and one that's easy to blur, especially at this hour, especially with a topic that wants to be dramatic. The blurring would feel better, it would also be wrong. So what does it mean for something to vanish? Depends who's asking, I suppose. The physics answer: a source is present in old data, absent in new data, with no confirmed explanation in existing mechanisms. The quieter answer, the one that doesn't go away when the physics answer is given, is something about what it means to leave no trace. To end in a way that produces no remnant, no echo, no record that you were ever there. Stars are not supposed to do that. They're supposed to leave something. A cooled dwarf, a collapsed core spinning out radio pulses, a nebula still glowing from the heat of whatever ended. Even the oldest, faintest objects tend to announce their presence in some way we can detect, given enough sensitivity. The ones in the catalogue didn't, or haven't yet. The distinction matters slightly, though at a certain point in the search it starts to feel academic. You can keep looking, and you should, and the VASCO team does, but at some point not found yet and not there start to occupy the same practical space. That's not a conclusion. I'm not sure this chapter has one, actually. It started as a question, what does it mean to vanish? And it's ending in roughly the same place, just with more company. More things to account for, more ways the question doesn't fully close, which is probably fine. Some questions are better held than answered. There's something I wasn't expecting when I first looked at one of these old catalogue pages. I thought it would feel significant, like looking at a crime scene photograph or a letter from someone who's since died. It didn't. It felt like looking at a spreadsheet. Columns, numbers, right ascension, declination, magnitude, plate number, a date, sometimes a note in the margin and a question mark or a letter indicating image quality. That's it. That's the whole record of a star that no longer exists in any detectable form. I kept waiting for the weight of it to arrive. It didn't, not right away. The US Naval Observatory's catalogue, the one that forms the historical baseline for the VASCO comparisons, was not built for posterity in any dramatic sense. It was built for navigation, for precision. The sky needed to be mapped accurately so that instruments depending on stellar positions would work, so ships would know where they were, so things could be calibrated against the fixed, reliable background of stars. The word fixed is doing something uncomfortable there in retrospect. The catalogue entries are dense with numbers and sparse with everything else. A star gets a designation, a string of digits that encodes its position in the sky, and that designation becomes functionally its identity in the record. Not a name, not a description, a location, encoded as a number, assigned to something that was assumed to be permanent. That assumption was built into the whole project. You don't note that a star exists and plan to check whether it keeps existing. You note it because it's there, and there is assumed to be a stable address. I've been thinking about the person who made 23,667. I made that number up, I want to be clear about that, but the persons didn't. Whoever catalogued these stars was working through a list, probably a long shift, probably with a loupe, leaning over a light table, glass plate underneath, pencil in hand. They were not thinking about posterity. They were doing a job. Maybe their back hurt. That's not a throwaway observation. It matters, I think, that the record was made without any awareness of what it would eventually reveal. The catalogue entries carry no weight of significance in themselves. The person writing them had no idea that 70 years later, a researcher would type coordinates into a database, find nothing at the other end, and start a chain of inquiry that is still running. The mundaneness of the original act is kind of staggering when you think about it long enough. What the catalogue entry contains in pure information terms is this. Photons from a specific direction in space hit a photographic plate on a specific date and caused a detectable chemical reaction. That's the observation. Everything else, star, source, object, is interpretation layered on top of the observation. Usually the interpretation is correct. A point source of light at stellar magnitude, stable across multiple exposures, is almost certainly a star. The alternative explanations, cosmic ray artifact, plate defect, brief transient, tend to produce slightly different signatures. Not always distinguishable, but usually. So the catalogue entry says, in shorthand, something was there, it was probably a star, here are its coordinates. Here is how bright it appeared to be. Filed, done. Next entry. The probably is buried so deep in the methodology that it stopped functioning as a qualifier. It became a certainty, because for the vast majority of entries it was. 70 years pass. This is the part that doesn't get enough attention, honestly. Not the discovery of the absence, that's the dramatic part, that's what gets written about. The 70 years in between. The catalogue sitting in a filing system or on a shelf, perfectly accurate, perfectly maintained, holding information that no one had any reason to question. The star, presumably, was doing whatever it was going to do. Burning, aging, moving toward whatever end it was going to have, and this is the strange part, completely indifferent to the fact that it was in a catalogue, that someone had written down its location and brightness and assumed it would stay. It didn't know it was documented. It didn't behave differently because of the record. The catalogue entry and the star's actual existence were always parallel things, never touching, only briefly corresponding on that one night when the plate was exposed and the photons landed and someone with a pencil wrote down what they found. And then the star ended, or changed, or collapsed, or did something we don't yet have a confirmed name for. And the catalogue entry remained, still accurate as a description of what was there, increasingly inaccurate as a description of what is there. That gap between was and is, that's the whole problem, compressed into a single number in a column on a page that nobody reads anymore. When researchers run the comparison now, the entry doesn't disappear from the old catalogue. It stays, the number stays, the coordinates stay, the magnitude stays. What changes is that those coordinates, when checked against current ski data, return nothing. So the entry is not a record of a star, it's a record of light. Light that's arrived on one night, hit a plate, caused a reaction, got written down. The light is gone. The reaction is fixed in silver on glass. The number persists in a database. And somewhere in that chain, between the light leaving and the number remaining, the star itself stopped being part of the story. Nobody set out to find missing stars. That's the part that keeps snagging on me when I think about how this whole investigation started. Not the discovery itself, but the shape of the path that led to it. It wasn't targeted. There was no hypothesis about stellar disappearance sitting in someone's desk drawer, waiting to be tested. The project that eventually surfaced these absences began as something much more open-ended, almost bureaucratic in its ambition. Compare the old sky to the new sky and see what changed. That's it. That was the initial frame. Not find vanished stars. Just look for differences. All kinds of differences. Things that appeared in recent data but weren't in old data. Things that were in old data and absent from new data. Anything that broke the assumption of a stable, consistent sky. The vanished stars were one output of that search. Not the only one, and at the start, not necessarily the most expected one. The project, VASCO formally, began taking shape around 2017. The core method was conceptually simple in the way that enormous undertakings sometimes are. Take a historical sky catalogue. Take a modern sky catalogue, cross-reference the two, and flag every source that appears in one but not the other. Simple in concept, staggering in scale. The historical baseline came primarily from the US Naval Observatory's catalogue of the northern sky, assembled from photographic plates taken mostly in the 1950s. The modern comparison came from PanSTARRS, a survey telescope in Hawaii that has been systematically imaging the sky since around 2010, with sensitivity and resolution that the 1950s equipment couldn't have approached. 600 million sources. That's how many objects appear in the historical catalogue. 600 million entries, each one a point of light recorded on glass somewhere over the course of several years, logged and numbered and filed. The initial comparison flagged around 150,000 discrepancies. Objects that were in the old catalogue are not clearly present in the new one, or vice versa. 150,000 cases where the two pictures of the sky didn't agree. Most of those 150,000 turned out to be nothing particularly strange. Catalogue artifacts, plate defects, known variable stars caught at different phases of their cycles, objects that had moved enough between surveys to land in slightly different catalogue positions and fail to match automatically. The machinery of large-scale astronomical surveys produces noise, and most of the initial discrepancies were noise, and the work of separating signal from noise in a dataset that large is, I'm going to say tedious, which is probably an understatement, and also probably not a word astronomers use about their own work, but from the outside it looks tedious, painstaking and slow. After filtering, after checking, after applying quality cuts and cross-referencing with other catalogues and manually examining the most promising candidates, the list came down, way down, to around 100 sources that couldn't be explained by any of the usual suspects. Not artifacts, not known variables, not catalogue mismatches, just present in 1950s data, absent in current data, no identified counterpart at any wavelength, no obvious explanation. 100 out of 600 million. Here's where the pacing of recognition gets strange, and I want to stay here for a minute because I think it gets skipped over too quickly in most accounts of this work. The recognition didn't happen all at once, it accumulated. The first discrepancies that survived filtering weren't greeted with alarm or excitement or any particular dramatic response. They were just flagged for further examination, the way you'd flag an anomalous reading in any dataset. A thing that doesn't fit the pattern gets set aside, examined more carefully, checked against additional data. Sometimes it resolves, sometimes it doesn't. The ones that didn't resolve kept accumulating, not quickly. Over months of work across a team distributed across multiple countries, Sweden, Spain, the United States, India, Ukraine, the list of genuinely unexplained absences grew slowly. Each one required its own round of checks. Each one had to have the mundane explanations ruled out before it could be considered a real candidate. And ruling out mundane explanations in astronomy is not a fast process. It involves requesting telescope time, waiting for that time to be granted, making new observations, processing the new data, comparing it to the old IO, and writing up what you found. The recognition that something genuinely strange was happening, that the candidates weren't resolving into familiar categories, arrived gradually enough that it probably didn't feel like a single moment of realization for anyone involved. More like a slow increase in the weight of the unexplained column, a growing sense that the mundane explanations were running out. I find that more interesting than the alternative would have been. A sudden discovery. Someone looks at a screen at a specific moment and sees the pattern, makes for a better story in the conventional sense. But the slow accumulation of not explained is actually what scientific recognition usually looks like. It's less a light turning on and more a room getting slightly incrementally brighter over a long time, until you realize at some point that you can see things you couldn't see before. There's a specific case that sharpens all of this considerably. On April 12, 1950, a photographic plate was exposed at Palomar Observatory. Standard procedure. The plate captured a region of sky and was developed and filed. Decades later, when researchers from the VASCO collaboration examined this plate carefully, not as part of the original survey but during targeted follow-up, they found something that the initial automated comparison had flagged but not fully resolved. 9-point sources, present on that plate in a small region of sky, all appearing within the same exposure. Half an hour later, a second plate of the same region was exposed. The 9 sources were gone, all of them, not faded, not moved, absent from the second plate entirely, and absent from every subsequent observation of that region at any wavelength. 9 simultaneous transients, appearing and disappearing within half an hour, leaving no detectable trace. This case, which was published as a separate study distinct from the broader VASCO catalogue work, represents something that has, as far as the literature indicates, no confirmed precedent in the history of astronomical observation. A single transient appearing and disappearing rapidly has multiple possible explanations. 9 of them appearing and disappearing simultaneously in the same region is harder to fit into existing frameworks, much harder. The researchers who examined it went through the standard list of candidates. Cosmic ray artifacts on the plate. Possible, but cosmic rays tend to produce specific signatures that these sources didn't match. Gravitational lensing events. Possible in principle, but the simultaneous nature of 9 separate events strains that explanation considerably. Satellite or aircraft reflections, the timing and the characteristics of the sources don't fit well. Fast radio bursts, these are known to produce brief intense signals, but not in a way that would explain 9 simultaneous optical point sources. Nothing on the standard list fits cleanly. The researchers noted this and published it as an open question, which is the correct response when you have data that doesn't resolve into existing categories. You don't reach for an exotic explanation just because the mundane ones don't work. You publish the data, describe what you found, note what you ruled out, and let the question stay open. The question is still open. What I keep returning to, and this might be slightly off topic, or maybe it's the whole point, I'm genuinely not sure, is the role that time plays in this kind of recognition. Not cosmic time, human time. The time it takes for a piece of data to travel from collected to examined to understood to questioned. Those 1950 plates sat in an archive for decades before anyone compared them systematically to modern sky data. The technology to make the comparison at scale didn't exist until recently. The catalogue infrastructure, the computational power to cross-reference hundreds of millions of sources, the survey telescopes sensitive enough to serve as a meaningful modern baseline, none of that existed in 1950 or 1970, or even 1990. The data was there. The tools to interrogate it weren't. So there's a sense in which the vanished stars were always vanished. They left no trace in the sky. But they were only discoverable once the gap between old data and new data became measurable. The absence was always there. The recognition of the absence required a specific moment in the development of astronomical infrastructure. That's not a remarkable insight, it makes the timeline feel different when you sit with it. The star ends at some point in the last 70 years or the last 70,000 years, and the record of it sits in a catalogue, and the sky moves on, and at some later point someone builds the tools to notice the discrepancy, and at some even later point someone actually runs the comparison and finds it. Recognition has its own speed, slower than light. Lower than most things, actually. It moves at the speed of available tools intersecting with available data, intersecting with someone deciding to look. The VASCO work is ongoing. The 100-odd candidates from the initial comparison are not a final number. They're a starting point for further observation and analysis. Some will probably resolve into known categories as more data arrives. Some might not. The 9 simultaneous transients from 1950 remain in a category of their own, still without satisfying explanation, still being considered. The team continues to look. New comparison surveys are being planned. Better filtering methods are being developed. The question of what happened to these sources, whether there's a single mechanism that explains most of them, whether some small fraction represent genuinely novel physics, whether the 9-source case belongs to a category that simply hasn't been named yet, is being worked on by people who are considerably more qualified to work on it than I am. What I can say, sitting with it from the outside, is that the pace of recognition in this investigation feels like the pace of the thing being investigated. Slow, incremental, full of false starts and resolved ambiguities and candidates that turned out to be noise, and somewhere in the remaining column, the ones that didn't resolve, something is waiting to be understood. What that something is, nobody has confirmed yet. The absence is real. The explanation isn't. I used to think I understood stellar death. I'd read enough about it, watched enough animations. The star runs out of fuel, it swells, it either fades quietly or it explodes spectacularly depending on its mass, and something is left behind. Simple enough, tidy. Then I spent time with the VASCO catalogue and realised I'd understood the script without understanding why the script exists. Why stars leave remnants. Why the ending always produces something. The reason matters here is not incidental. A star is, at its core, and I mean that almost literally, a negotiation. Gravity pulling inward, radiation pressure pushing outward. These two forces spend millions or billions of years in a kind of standoff, and the star exists in the space that standoff creates. Bright, hot, fusing hydrogen into helium in its core, releasing energy, maintaining the outward pressure that keeps it from collapsing under its own weight. This continues until the fuel runs out. When it does, the negotiation ends. Gravity wins. What happens next depends almost entirely on how much mass the star had to begin with. A low-mass star, something like our Sun give or take, runs out of hydrogen in its core and starts fusing helium instead, swelling outward into a red giant in the process. Eventually the helium runs out too. Without the energy to maintain outward pressure, the outer layers drift away into space as a slow expanding shell of gas, a planetary nebula, which is a misleading name that stuck around from a time when the terminology was less careful. What's left at the centre is a white dwarf, a dense hot remnant, roughly Earth-sized, no longer fusing anything, just slowly radiating away its stored heat over billions of years. This process leaves things behind. Lots lots of things. The planetary nebula is detectable. The white dwarf is detectable. The whole ending is, in astronomical terms, loud. For a more massive star, the ending is louder still. When a massive star, something 8 or more times the mass of the Sun, exhausts its fuel, the collapse is faster and more violent. The core, no longer supported by fusion energy, implodes in a fraction of a second. The infalling outer layers hit the dense core and rebound outward in a shock wave. The result is a supernova, one of the most energetic events in the observable universe, briefly outshining entire galaxies, visible across enormous distances, leaving behind either a neutron star or, if the original star was massive enough, a black hole. Either way, there's a remnant. A neutron star is detectable, often loudly so. Many of them emit regular pulses of radio waves as they spin, which is how we find them. A black hole formed from a supernova is surrounded by the debris of the explosion, an expanding shell of ejected material that glows for centuries. We can find these. We have found thousands of them. The point is that the grammar of stellar death, and I keep coming back to grammar because that's genuinely what it feels like, a set of rules the universe seems to follow, always produces a sentence, always leaves something for us to read. Even stars that die before telescopes existed left remnants we can find now. The Crab Nebula, that expanding cloud of gas visible in Taurus, is the remnant of a supernova observed by Chinese astronomers in 1054, nearly 1,000 years ago. The star is gone. What it left behind is still there, still glowing, still detectable. This is what makes the VASCO candidates genuinely strange. Not just that the stars are absent, that they're absent without leaving the things they were supposed to leave. No expanding gas shell, no white dwarf at the coordinates, no neutron star spinning out radio pulses, no X-ray source indicating a black hole accreting material from a companion. Nothing at any wavelength. The ending, if there was an ending, produced no sentence, no remnant, no detectable trace of a process that should, by all established understanding of how stars work, have produced something. And here is where I want to be careful because it's easy to overstate this. Most of the VASCO candidates probably have mundane explanations that haven't been confirmed yet. A variable star at extreme minimum, a cataloguing error from 1950, a supernova whose remnant has already faded below detectability, which can happen faster than you'd think for certain types in certain environments. The absence of a detected remnant is not the same as the confirmed absence of a remnant. We might just not be looking with the right instrument at the right wavelength with enough sensitivity. That's a real possibility. I want to hold it honestly rather than letting the mystery pull harder than the evidence justifies. But there is a theoretical mechanism, not invented for the occasion, not exotic in the science fiction sense, but a real prediction from stellar physics that would produce exactly this kind of traceless ending. A massive star under specific conditions could skip the supernova stage entirely. Instead of the core imploding and rebounding in a shockwave that blows the outer layers off, the collapse continues. Everything falls inward. The black hole forms not from the remnant of an explosion but from the total collapse of the whole star. No ejector, no shockwave, no expanding remnant, just the star, and then the absence of the star. This is called a failed supernova, or sometimes direct collapse. It's considered rare. Estimates vary, but the fraction of massive stars that end this way, if any do, is thought to be small. Maybe a few percent, maybe less. Here is my actual opinion on this, for whatever it's worth, which is probably not much. The existence of a theoretical mechanism that predicts exactly what we're observing in these candidates is not confirmation that the mechanism is responsible, but it is interesting in a specific way, not the flashy interesting of a dramatic discovery, more the quieter interesting of a prediction and an observation landing in the same place and making you wonder if they're pointing at each other. They might be, they might not be. The VASCO team is careful about this. The papers are careful about this. The mechanism is mentioned as a candidate, not a conclusion, which is the right call, probably, though sitting with candidate, not conclusion, is harder than it sounds when the alternative, a traceless stellar death, is this structurally strange. The grammar has a possible exception. Whether these stars are actually the exception, or whether they're something else entirely, or whether the records from 1950 are simply wrong in ways that haven't been identified yet, that question is still open. The ending was supposed to leave something. In these cases it didn't. Or it left something we can't find, which amounts to the same problem viewed from here. 70 years sounds like a long time until you put it next to something that isn't. The light from Proxima Centauri, the nearest star to our Sun, a dim red dwarf sitting about 4.2 light-years away, takes just over 4 years to reach us, meaning that when you look at it on a clear night you are seeing it as it was roughly 4 years ago, which feels like a manageable delay, almost intimate by the cosmic standards, the kind of lag you could almost forgive. But Proxima is the closest one. Everything else is farther. The stars in the Orion constellation that you can see without any equipment sit somewhere between 250 and 1,300 light-years away, which means the light arriving in your eye tonight left those stars somewhere between the early medieval period and the late Roman era, before any of the languages currently spoken on this planet existed in recognizable form. And those stars have had between 250 and 1,300 years since that light left to change in ways we haven't seen yet, ways that are already travelling toward us and won't arrive for a long time. 70 years in that context is genuinely nothing. A breath, less than a breath, a fraction of one, and yet the entire VASCO investigation is built across that span. 70 years between the old plates and the new observations. 70 years is the window within which these stars disappeared, or rather, it's the window within which we confirmed they had disappeared, which is a different thing, because the actual moment of disappearance could have been at any point inside that window or well before it. A star recorded in 1950 and absent in 2019 could have vanished in 1951, or 1987, or 2015. The comparison tells you it was there then and gone now, but the 70 years between is not a continuous observation. It's 2 snapshots with a long gap in between, and anything could have happened in the gap. And the gap is, from the star's perspective, if we can use that phrase loosely, essentially instantaneous. This is the thing about 70 years that keeps shifting on me slightly. From one angle it feels like a long human stretch of time, long enough that most people alive in 1950 are gone now, long enough that the technology, the politics, the languages people used to describe the sky have all shifted considerably. From another angle it's a measurement interval so short that for most astrophysical processes it would barely register as a rounding error. The universe is approximately 13.8 billion years old, give or take a few 100 million, which is itself a remarkable thing to be able to say with any confidence at all. The stars in the VASCO catalogue that have since vanished were, most of them almost certainly, far older than 70 years. A star like our Sun lives for roughly 10 billion years. More massive stars burn hotter and faster and live shorter lives. But even the shortest-lived massive stars, the ones that exhaust their fuel in a few million years, are living timescales that make 70 years look like an afternoon. So when we say a star vanished within a 70-year window, we are saying something precise but also strange. A thing that existed for millions or billions of years ended, or transformed or collapsed, during a period so short relative to its own lifespan that if you scaled the star's life down to a single human year, the window of its disappearance would be measured in seconds. Less than seconds, actually. I did the rough math on this once and then immediately wasn't sure I'd done it right, but the order of magnitude holds. 70 years out of 10 million is vanishingly, almost uncomfortably small. The central oddity of this, and I've been circling it, I realise, which wasn't entirely intentional, is that the 70-year window feels significant to us because it spans human memory, human record-keeping, human institutional continuity. The Naval Observatory plates from 1950 still exist. The people who made them mostly don't. The comparison is possible because the glass survived. If the plates had been made in 1850 instead of 1950, the comparison would be harder, the technology gap wider, the archival challenges greater, the systematic differences between then and now more difficult to account for. If they'd been made in 1750, probably impossible by current methods. The 70 years is not a meaningful astronomical interval. It's a meaningful human institutional interval, the span across which careful record-keeping can be maintained, cross-referenced, digitized, and compared without the methodological uncertainties becoming unmanageable. We found these absences because we happened to be making careful records at exactly the right time, and we happened to develop the comparison tools within the same institutional lifespan as the original records. That's a contingency, not a design, and it means there are almost certainly other stars that vanished before 1950, before careful photographic surveys, before anyone was keeping the kind of records that allow for this comparison, and those disappearances are not recoverable. They happened in the gap before the window opened. 70 years is not very long, it just happens to be long enough. Let me start with the fact itself, because I keep wanting to set it up, and I'm not sure it needs setting up. It needs to be said plainly first, and then we can sit with it. On April 12, 1950, a photographic plate was exposed at Palomar Observatory, a region of sky, standard exposure. The plate was developed, filed, given a number, and stored. Decades later, when researchers examined this plate carefully as part of the VASCO follow-up work, they found 9 faint point sources clustered in a small area. 9 objects present on that plate that were not in the modern sky data for the same region, and not in any other historical observation of that region either before or after April 12, 1950. A second plate of the same region exposed the same night, roughly half an hour later. The 9 sources were gone. All 9, not 8, not most of them. All 9, within half an hour, leaving nothing detectable in any subsequent observation at any wavelength. That's the fact. That's what happened, or what the data shows happened, which is as close to what happened as we can get. I've read the paper on this a few times now, and I want to be honest about something. I'm still not sure I've fully processed it. Not because the data is complicated, and it's actually pretty straightforward as astronomical data goes. A set of point sources on a glass plate that don't appear anywhere else. But because every time I try to hold it steadily in mind, some part of my brain starts reaching for a familiar shape to put it in, and there isn't one. The familiar shapes don't fit. A single transient appearing and disappearing, fine. There are known mechanisms. Gamma ray bursts can produce brief optical counterparts. Gravitational lensing can temporarily magnify a distant source into visibility and then let it fade. Variable stars can brighten dramatically and then dim below the detection threshold. These are real phenomena with understood physics and observed examples. 9 simultaneous transients, same region, same plate, gone within 30 minutes. That's, and I realize I keep returning to this, but it keeps being true, that's a different category of problem. The known mechanisms don't scale to 9 simultaneous events in the same small patch of sky. You can invoke them for 1. Invoking them for 9 at once requires either 9 separate coincidences happening in the same place at the same time, which is the kind of probability that starts to feel like it's arguing against itself, or a single mechanism that could produce 9 simultaneous transient optical sources and then remove all of them within half an hour, leaving no detectable remnant. No known mechanism does that, not one that's been confirmed anyway. The researchers went through the candidates carefully. Cosmic ray artifacts. Cosmic rays hitting the photographic emulsion can produce spots that resemble point sources. This is a real and common source of false positives in old plate data, and ruling it out requires looking at the morphology of the sources carefully. Cosmic ray hits tend to produce slightly elongated or irregular shapes, or clusters that follow the grain structure of the emulsion, and they tend to appear more randomly distributed rather than clustered in a region with any apparent spatial coherence. The 9 sources didn't match the cosmic ray artifact profile well. Not conclusively ruled out, but not a clean fit. Satellite reflections, by 1950, this is actually not quite the issue it became later. Sputnik wasn't launched until 1957. There were experimental rockets and high-altitude balloons, but nothing in sustained orbit that would produce 9 simultaneous reflective sources in a small sky region. The geometry doesn't work anyway. Satellite or aircraft reflections tend to produce streaks or trails rather than point sources, and they don't replicate across a short re-exposure of the same field without appearing again. Gravitational lensing, this one is interesting to think about and then put down. Gravitational lensing can produce multiple images of a background source when a massive foreground object sits between us and it at the right alignment. But 9 separate lensed sources appearing and disappearing simultaneously would require 9 separate alignment events, or one extraordinarily unusual lensing configuration that isn't really supported by the geometry of the field it was considered. It doesn't fit. Fast radio bursts. There's a version of this explanation that almost works in the sense that FRBs are brief, intense, not fully understood. And some have associated optical components. But the optical signatures that have been detected alongside FRBs don't match the characteristics of what's on the plate, and 9 simultaneous events from a single FRB source doesn't correspond to anything in the observed phenomenology of these events. So you go through the list one by one, and each candidate either doesn't fit or fits one of the 9 but not all 9, and at the end of the list you're left with nothing confirmed. An open file, 9 sources on a glass plate from 1950 that remain, as of the most recent literature I've been able to find without a satisfying explanation. There are 2 directions people tend to go at this point, and I think it's worth being clear about both of them rather than pretending only one exists. The first is the conservative scientific response, which is, the explanation probably exists within known physics. We just haven't identified it yet. Photographic plate artifacts can be subtle and varied. The original plate should be examined with every available modern tool before any exotic explanation is entertained. The absence of a confirmed mundane explanation is not evidence of a non-mundane one. It's evidence that more investigation is needed. This is the correct methodological stance, and I don't want to undercut it. The second is the one that some of the researchers involved with VASCO have been willing to mention carefully, with appropriate hedging, in published work, which is that objects appearing and disappearing on short timescales without identified natural counterparts are exactly the kind of signal that a sufficiently advanced technological civilization might, in certain theoretical frameworks, produce. Not because anyone is claiming that's what happened on April 12, 1950, but because if you're going to think about what kinds of astronomical observations might be indicative of something non-natural, Brief simultaneous transients with no remnant it's on the list. It fits the category. The VASCO team has been clear that this is speculative, very speculative. It appears in their papers more as a motivation for the search than as a proposed explanation for any specific candidate. The logic is, if such signals exist, this kind of survey would be how you find them, so it's worth looking, even if the expected yield is 0 or near 0. I find that intellectually honest in a way that I appreciate. They're not claiming to have found aliens. They're saying, here is a search method that would be sensitive to a certain class of hypothetical signal, and here are the anomalies that search method turned up, and here is the very large uncertainty around what those anomalies represent. That's a defensible position. It just doesn't make the 9 sources any less strange to sit with. I want to describe the image itself for a minute, because I think the abstraction of 9-point sources on a photographic plate doesn't quite land the way the actual image does. The plate, or the digitized scan of it, which is what's actually accessible, shows a field of stars. Hundreds of them, various brightnesses, the usual dense scatter of a reasonably populated region of sky. And in one area of the field, 9 faint objects that are not individually remarkable. They're not bright, they're not doing anything visually dramatic, they're just present. Small, faint, clustered loosely in a region maybe a few arc-minutes across. And then, on the second plate, the same field, half an hour later, they're not there. The rest of the field looks the same. The other stars are in their positions, same brightnesses, same everything. Just those 9 gone. It's a strangely quiet image for something this unexplained. I think I expected it to look more dramatic somehow, and it doesn't. It looks like a normal patch of sky with 9 things in it, and then a normal patch of sky without them. The ordinariness of the visual is, I don't know, it bothers me slightly more than a dramatic image would have. A dramatic image would feel like it was showing you something strange. This just looks like a calibration error or a smudge until you understand what you're looking at, and then it doesn't look like that at all anymore. It looks like a question with no current answer printed on glass from 70 years ago. There's a researcher I keep thinking about when I sit with this case. Not because of anything specific they said, but because of the situation they're in. Being the person who found this, who looked at the plate carefully enough to notice the 9 sources, and then looked at the second plate and found them gone, and then had to decide what to do with that information. The decision was, publish it. Describe what was found, describe what was ruled out, describe what remains unexplained, and let other people engage with it, which is the right decision. But there's a period before that decision. The period of sitting with data that doesn't fit anything you know, before you've written it up, before anyone else has seen it, that I find interesting to think about. That's a specific kind of uncomfortable. Not frightening, not exciting exactly, more like the feeling of holding something fragile that you're not sure how to put down without breaking it. 9 things appeared on a plate. Half an hour later they were gone. No one saw it happen. The plate saw it, in the sense that the emulsion recorded the photons, and then the second plate recorded their absence. The actual event, whatever it was, occurred without a human witness. The recognition of the event came decades later in an archive, under examination that the original observers couldn't have anticipated. Whatever the 9 sources were, and I'm not going to guess, there's no responsible guess to make here, they were there, and then they weren't, and we have the glass to prove it, and we don't have much else. That's where this sits. Still, quietly. On a shelf somewhere, probably, in a climate-controlled room that smells faintly of the specific chemical staleness of old archival materials. That particular smell that old paper and old photographs share, slightly sweet and slightly sour at once. The plate is still there, the sources aren't, and the gap between those 2 facts is, for now, the whole story. There's a specific kind of thinking that happens after lunch, and not sharp, not sluggish exactly, just settled. Like the mind has been given permission to move at its own pace for a while. I've been sitting with this chapter for about an hour now, and I think that state is actually the right one for what direct collapse requires. It's not a dramatic concept. It doesn't need urgency. It needs a certain willingness to follow something slow and total down to its end. So, direct collapse. Start with what a star is doing structurally at any given moment during its life. The core is fusing, hydrogen into helium in the early stages, helium into carbon and oxygen later, and for the most massive stars, a sequence of further fusions that produce neon, silicon, sulfur, and eventually iron. Each stage produces energy. The energy radiates outward, creating the pressure that holds the star up against its own gravity. This is the negotiation mentioned earlier. Inward pull, outward push, the star existing in the stable middle of those two forces for as long as the fuel holds. Iron is where the sequence stops. Fusing iron doesn't release energy, it absorbs it. So when an iron core builds up at the center of a massive star, it's building up dead weight. Inert. Not contributing to the outward pressure. Just sitting there, getting heavier as the layers above it continue fusing and raining more iron down onto it. The iron core grows. It grows until it reaches a specific threshold, roughly 1.4 times the mass of our Sun, which is known as the Chandrasekhar limit, named after the physicist who calculated it in the 1930s, reportedly while sitting on a ship crossing the Atlantic, which is a detail I find completely unnecessary but also somehow essential. And at that point the electron degeneracy pressure that was holding the core up can no longer support the weight above it. The core collapses in less than a second, something like a quarter of a second actually, for the initial collapse. A core roughly the size of Earth compressing down to something roughly the size of a city. The density becomes extraordinary. Protons and electrons are forced together into neutrons. The core becomes briefly a proto-neutron star. In the standard picture, the one that holds for most massive stars, what happens next is the explosion. The infalling outer layers of the star, travelling inward at a significant fraction of the speed of light, hit the newly formed neutron star core and rebound. The rebound drives a shockwave outward through the star. The shockwave stalls almost immediately because it's losing energy to the dense stellar material around it. Then, and this is the part that took decades of theoretical work to understand and is still not fully settled, neutrinos save it. The collapsing core produces an extraordinary flux of neutrinos. Neutrinos almost never interact with matter. They pass through everything, which is why detecting them requires enormous underground tanks of extremely pure water or ice, and even then you're catching only a tiny fraction of the ones passing through. But at the densities present just after core collapse, even neutrinos interact enough to deposit a small fraction of their energy into the stalled shockwave. That energy revives it. The shockwave powers outward. The outer layers of the star are ejected at high velocity into the surrounding space. Supernova. The whole sequence, from core collapse to explosion, takes seconds to minutes. The star that existed for millions of years ends in the time it takes to eat lunch. Now, direct collapse is what happens when that revival doesn't occur. The neutrinos are produced, the shockwave stalls, but the revival fails. The energy deposition isn't sufficient for reasons that depend on the specific mass, composition, and rotation of the star, and the shockwave doesn't recover. Instead, the material that should have been ejected continues falling inward. More mass accretes onto the proto-neutron star. The proto-neutron star exceeds its own mass limit, neutron degeneracy pressure fails, and collapses further into a black hole, and the outer layers of the star, without a shockwave to push them away, follow. Everything falls in. The black hole forms not from a neutron star remnant, but from the total collapse of the entire stellar mass, more or less continuously. No ejector, no expanding shell, no neutron star left behind to spin and pulse. The energy that would have gone into the explosion goes instead, mostly, into neutrinos that escape in a brief, undetectable burst, and gravitational waves too faint and brief to have been caught by any current detector, and that's it. That's the entire external signature of an event that just ended something millions of times more massive than Earth. The question of whether this actually happens, whether direct collapse is a real process and not just a theoretical possibility, has been approached from a few directions. One is theoretical modelling. Simulations of core collapse supernovae have been getting more sophisticated for decades, and certain regions of parameter space, certain combinations of stellar mass, metallicity, rotation rate, consistently fail to produce successful explosions in the models. The shockwave stalls and doesn't recover. The models suggest that for stars above a certain mass threshold, direct collapse may be the expected outcome rather than the exception. The second is observational. There have been a small number of cases, very small, a handful, where astronomers watched a massive star and then found it gone in subsequent observations, with no detected supernova in the intervening period. The most discussed case involves a star in a nearby galaxy that was being monitored as part of a survey, present in one observation set, absent in the next, with no reported supernova in that galaxy during the interval. This is not confirmed direct collapse, it's a candidate. The language around it in the literature is careful for good reason. There are alternative explanations, including the star being obscured by dust produced in a failed explosion, which is different from a true silent collapse. I want to be careful here because this is exactly the kind of topic where the interesting possibility can start doing more narrative work than the evidence actually supports, and I've probably let that happen slightly in earlier chapters, and I'm trying not to let it happen here. What the evidence supports is direct collapse is theoretically well motivated. It may have been observed in one or two candidate cases. It would produce the kind of traceless disappearance seen in the VASCO catalogue, and the rate at which it's expected to occur is uncertain but probably low. A few % of massive star deaths maybe less. The connection to the VASCO candidates is plausible and worth investigating. It is not established. There's a physical detail about direct collapse that I keep returning to, not because it changes the science, but because it keeps clarifying something about the scale of what we're talking about. A star undergoing direct collapse, a star that has spent millions of years burning, that has existed as a visible object in the sky, that has been there long enough to be photographed and catalogued, takes roughly half a second to collapse its core. The full collapse of the outer layers into the black hole takes longer, maybe seconds to minutes depending on the mass and structure, but the moment of no return, the moment after which the outcome is fixed, is measured in fractions of a second, millions of years, then half a second. There's no good way to hold those two timescales in the same thought. I've tried. You can say the words millions of years, half a second, and understand them individually, but the ratio doesn't land as a felt thing. It just sits there, technically accurate, emotionally inert. What helps slightly is thinking about what half a second actually is in the context of the star. The star doesn't experience it as a short time. The star doesn't experience anything. But the physical processes happening in that half second are operating at speeds. The core collapse velocity approaches significant fractions of the speed of light that are so far outside ordinary physical intuition that half a second is almost an arbitrary label. What's happening in that half second involves more energy than our sun will release in its entire 10 billion year lifetime. The timescale is short. The event is not small. What direct collapse would look like from here, from a planet orbiting a star 4 light years from the nearest neighbour, watching the sky with instruments of various sensitivities, is nothing. Or as close to nothing as makes no practical difference. No optical brightening. The star doesn't flare before it goes. There's no shockwave reaching the surface to produce a precursor signal. No radio pulse from a newly formed neutron star, because there is no neutron star. No expanding nebula appearing in the weeks and months afterward, because there's no ejector. A gravitational wave signal, yes, but brief and faint, far below what current detectors can pick up at stellar distances beyond our immediate galactic neighbourhood. A neutrino burst, yes, but lasting less than 10 seconds at a flux that would be undetectable except in the very closest cases. The star is there, then the star is not there. If you weren't watching at the exact moment, and you almost certainly weren't, because continuous monitoring of individual stars across the whole sky simultaneously is not something we do, you would just notice eventually that a star you thought was there isn't anymore. When you next look, whenever that is, which is more or less exactly what the VASCO comparison found. Stars that were there in 1950, not there now, with nothing in between to indicate what happened. Direct collapse is not the confirmed explanation for those stars, but it is, and I keep coming back to this, I realise, which is maybe what the evidence does when it points consistently in one direction without quite arriving. It is the explanation that requires no additions to known physics. No new mechanisms, no exotic processes, just a known theoretical pathway, operating at the rare end of its expected frequency, producing exactly the observational signature we're looking at. That's not proof, it's just a shape that fits. And sometimes, in a long investigation, a shape that fits is the most you have for a while. Cloud is dense enough, the star disappears. The dust explanation feels reasonable the first time you hear it. A cloud of interstellar dust drifts between us and a star. The star dims. If the cloud is dense enough, the star disappears below the detection threshold entirely. The old catalogue caught it before the cloud arrived. The new survey finds nothing. Case closed, mundane next. It's a satisfying explanation. Tidy. It doesn't require new physics or uncomfortable questions about stellar endpoints. Dust exists everywhere in the galaxy. Dense molecular clouds, diffuse hazes of carbon and silicate grains, the remnants of earlier stellar deaths, and it absorbs and scatters light with well-understood efficiency. The galaxy is not a clear medium. Things get obscured. The problem is the math. Interstellar clouds move, not quickly by human standards. Typical velocities relative to surrounding stars are tens of kilometers per second, sometimes more, sometimes less. But they move continuously, and that motion is measurable. A cloud that drifts in front of a star and blocks it will, given enough time, drift past. The star reappears. This is not a theoretical prediction, it's an observed phenomenon. We have watched stars dim and brighten again as intervening material moves across the line of sight. So if dust is the explanation for the VASCO candidates, the stars should eventually come back. They haven't. The candidates that have been monitored across multiple observation epochs, checked not just in the initial pan-stars comparison, but in subsequent targeted observations with larger telescopes, have not reappeared. Not at optical wavelengths, which dust would block. Not at infrared wavelengths, which dust would not block because dust that absorbs visible light re-emits it as heat radiation that infrared instruments can detect. Not at radio wavelengths, which pass through dust almost entirely unimpeded. A star hidden behind a dust cloud is still a star. it's still producing light at every wavelength. The dust shifts that light around spectrally, absorbing the blue end, letting the red end through, re-emitting in the infrared, but it doesn't make the star disappear from all wavelengths simultaneously. Nothing at infrared, nothing at radio. That's not a star behind dust. That's something else. There's a related explanation that's slightly more sophisticated and gets proposed occasionally. Not a foreground dust cloud, but dust produced by the star itself in its final stages. Some massive stars in the period before a terminal event shed enormous quantities of material. Dense stellar winds, episodic eruptions, shells of gas and dust expelled over decades or centuries. If a star produced a thick enough cocoon of its own material, and then underwent some kind of terminal event, a faint supernova, a failed explosion, the cocoon could absorb the light from the event entirely, preventing it from reaching us. This one is harder to rule out cleanly. It's been invoked in specific contexts. There are cases of supernovae that were heavily obscured by the circumstellar material and only detected at radio wavelengths long after the optical event would have faded. The physics is real, but it runs into the same infrared problem. A cocoon of circumstellar dust absorbing a supernova's optical output would re-radiate the absorbed energy as infrared, and that infrared signature would be detectable, would persist for years to decades depending on the mass of the cocoon, and would be identifiable as something unusual at the coordinates of the vanished source. The VASCO candidates that have been examined carefully don't show this. The infrared is quiet. The coordinates are quiet at every wavelength that's been checked, which either means the circumstellar dust scenario doesn't apply, or the dust cocoon was somehow so optically and infrared thick that even the irradiated energy was absorbed and thermalized at lower temperatures, which would push the emission to even longer wavelengths, millimeter and radio, which have also been checked in some cases and found empty. At some point, the dust explanation requires adding qualifications that start to strain against each other. The dust must be thick enough to block optical emission completely, also thick enough to absorb and re-radiate the infrared without producing a detectable signature, also somehow not detectable at radio. Each additional qualification is physically possible in isolation. Together, they describe a set of conditions that becomes increasingly unlikely for any given source. There's something useful about a failed explanation, though, and I don't mean that in a falsely optimistic way, more just as a practical observation about how investigation works. Ruling out dust doesn't tell you what happened to these stars. It doesn't bring you closer to a confirmed mechanism. It just removes one exit from a room that still has other exits, and the room is smaller than it was. That's the actual value, not an answer, a constraint. The same process, testing an explanation, finding it insufficient, noting the insufficiency and moving on, has been applied to the other mundane candidates. Variable stars at minimum, catalogue artifacts, gravitational lensing events, each one ruled out or rendered insufficient for the specific characteristics of the surviving candidates, each ruling out a small reduction in the space of possible explanations. What's left after all the mundane candidates have been tested and found wanting, not definitively, not in every case, but sufficiently, is a smaller and less comfortable set of possibilities. Possibilities that don't have the same immediate intuitive appeal as a drifting dust cloud. Dust would have been easier. It moves, it obscures, it passes, the star comes back. Clean mechanism, no remnant problem, no challenge to existing frameworks. But the infrared is quiet, the radio's quiet, the stars haven't come back. Dust explains a lot of things in this galaxy. These particular absences it doesn't explain. Or doesn't explain well enough to close the file on, which in an investigation like this amounts to the same thing. Mira disappears every 11 months, not forever. It comes back reliably, on a schedule that Johannes Hevelius worked out in the 17th century after watching it long enough to trust the pattern. But if you happen to look at the right patch of Cetus at the wrong point in its cycle, you'd find nothing where a reasonably bright star should be. You'd check your chart, check again. The star wouldn't be there. Before anyone understood what Mira was doing, this must have been... I keep trying to imagine the first time someone noticed it was gone, and I can't quite get there. The sky was supposed to be fixed, eternal. The church said so, Aristotle said so. And here was a star that kept not being there, then being there again, then not, on a cycle that nobody had a framework for. It was named Mira, wonderful in Latin, which is either a beautiful choice or a slightly nervous one, depending on how you read it. Mira is a red giant, old by stellar standards, around 6 billion years into a life that's winding down, its outer layers expanded and unstable, pulsating inward and outward on a period of roughly 332 days. When it expands, it brightens. When it contracts, it dims, sometimes below the naked eye threshold, sometimes well below it, down to magnitudes that require a decent telescope to detect. The physics of why it does this involves the opacity of ionized helium in the star's outer layers, which changes as the layers expand and cool and then compress and heat again, creating a feedback loop that sustains the pulsation over timescales far longer than a human life. The mechanism is understood now. It was understood, at least in outline, by the mid-20th century. Mira is not mysterious anymore exactly. It's well characterized. There are entire catalogues of Mira-type variables, thousands of them, their periods and amplitude ranges logged and cross-referenced. Chi Cygni is another one. It pulsates from magnitude 3.3, easily visible to the naked eye on a clear night, to magnitude 14.2, which requires a moderately large amateur telescope to detect. That's a factor of roughly 10,000 in apparent brightness between maximum and minimum. The same star, same position, same coordinates, just sometimes there, sometimes not, depending entirely on where it is in its roughly 408-day cycle. The first person to notice Chi Cygni fading probably thought something had gone wrong. The reason I want to stay here for a while, with Mira, with Chi Cygni, with the whole category of long-period variables, is not because they explain the VASCO candidates. They don't. The VASCO team checked this. Variable stars at minimum are still detectable at infrared wavelengths, even when they've faded below optical detection, because the star is still there, still radiating, just cooler and dimmer than at maximum. The VASCO candidates aren't showing up in infrared. They're not showing up anywhere, so variables at minimum don't account for them. But variables at minimum are the closest natural analogue to what the VASCO candidates look like from the outside, and sitting with that analogue for a while makes the difference between the two sharper and more specific. A star at minimum is absent from the optical sky temporarily. It will return. Its absence is cyclical, predictable, embedded in a mechanism that leaves the star itself intact. The absence is, in a sense, performed. The star is doing something that produces the appearance of absence without actually being absent. The VASCO candidates are absent in a different way, not performing absence, not cycling, not temporarily below threshold while remaining infrared detectable, just gone in a way that doesn't resolve into any known pattern of temporary disappearance, and hasn't resolved across the decades since the original observation. The gap between those two kinds of absence is the whole problem compressed into a comparison. There's a third category worth mentioning, not Mira types, but something adjacent. Stars that have been observed to fade dramatically and not fully recover on any timescale we've been able to monitor. Betelgeuse did something like this in 2019 and 2020, dimming to roughly 40% of its normal brightness over several months. The Great Dimming, as it got called, which attracted an enormous amount of attention, including widespread speculation that it was about to go supernova, which it did not do. The dimming turned out to be a combination of a surface temperature drop and a cloud of dust produced by a large ejected mass of stellar material that temporarily obscured part of the star's disk. Betelgeuse came back. It's actually brighter now than it was before the dimming event, which is its own interesting detail. But the Great Dimming is useful here because it shows how quickly a star can change its apparent brightness, over months, not millennia, and because it shows how a dust-related dimming event produces a specific detectable signature that is distinguishable from a true absence. The dust that obscured Betelgeuse was detectable. The temperature change was measurable. The star remained present at infrared wavelengths throughout. This is the pattern with every well-characterized stellar dimming event we have. The mechanism leaves fingerprints. The star doesn't disappear cleanly. It leaves traces of what happened to it, photons at some wavelength that carry information about the process. There's something about the long-period variables, Mira especially, that I keep not quite finishing a thought about, and I want to try to land it even if it comes out slightly sideways. Mira's cycle has been observed for centuries. The period has been measured, refined, checked against theory, and the physics behind it is, at this point, about as well understood as stellar physics gets. It is one of the success stories of astrophysics, a phenomenon that was once confusing and slightly alarming, resolved into a clean mechanism that explains the observations completely. The VASCO candidates are, right now, at the position Mira was in before anyone understood what was happening. Observed absences, no confirmed mechanism. The explanation is somewhere. It exists, presumably, within the universe's actual physical processes. But we don't have it yet. We're at the stage of ruling things out rather than confirming anything. What I find myself resisting, and I'm not sure the resistance is warranted, is the assumption that the explanation will turn out to be as clean as Mira's. Mira's explanation required no new physics. It required understanding the opacity behavior of ionized helium in pulsating stellar envelopes, which is not simple, but it's physics that was already in the toolkit. The explanation fit within the existing framework once the right piece of the framework was applied. The VASCO candidates might resolve that way. Probably most of them will, into known categories once the right data is available or the right analysis is applied. But some fraction, and it's unclear how large that fraction is, which is itself a meaningful uncertainty, might be pointing at something that doesn't fit as cleanly. Something that requires not just applying existing physics more carefully, but expanding what existing physics means. Or maybe not. Maybe they're all variables at unusual phases, or catalogue artifacts, or dust scenarios that the current multi-wavelength data isn't sensitive enough to detect at these distances. Maybe. It's possible. I keep that possibility open because it's the honest thing to do. But there's another possibility, one that involves not stellar physics at all, not any natural process, not anything in the framework we use to describe how stars live and die, that some of the researchers involved with VASCO have been willing to name carefully in print. I'm not going to get into it properly right now. The idea deserves more space than what's left here. And I want to approach it without rushing, because the moment you rush toward it, it stops being a scientific question and starts being something else, which is not what it is. For now, Mira comes back. The VASCO sources haven't. That difference is the whole weight of the question, and where the weight eventually settles is something the next few years of observation might begin to clarify. Or might not. Science moves at its own pace, which is rarely the pace you'd choose for it. The US Naval Observatory in 1950 was not doing astronomy in the way the word tends to get used now. Curious, exploratory, pointed at questions about the universe's nature or origin. It was doing something older and more practical. It was keeping time, tracking positions, maintaining the kind of precise celestial records that navies and air forces and anyone who needed to know exactly where they were on the surface of the Earth depended on. The sky, in this context, was infrastructure. The photographic sky survey that produced the plates now central to the VASCO investigation was called the Palomar Observatory Sky Survey, POSS in the shorthand, and it was undertaken collaboratively between the National Geographic Society and Caltech, using the 48-inch Samuel Oskin Schmidt telescope at Palomar Mountain in California. It ran primarily between 1950 and 1957. The goal was straightforward: photograph the entire northern sky systematically in 2 wavelength bands to a depth and resolution that hadn't been achieved before. Every region of sky north of roughly -27 degrees declination covered twice, once in blue-sensitive emulsion, once in red-sensitive emulsion, on large glass plates, each covering about 6 by 6 degrees of sky. The Naval Observatory catalogue that forms the comparison baseline drew heavily on this survey and subsequent ones like it. The plates were not made for posterity in any self-conscious sense. They were made because a complete, accurate, deep record of the sky's point sources was operationally useful. Navigation, astrometry, calibration of instruments, the kind of work that happens in the background of more visible science, maintaining the infrastructure that makes other things possible. The people doing this work were not for the most part asking large questions. They were doing careful, skilled, repetitive observational work, loading plates, making exposures, developing them, examining them under magnifying glasses, recording positions and magnitudes in logbooks, checking measurements against previous records. The kind of work that requires sustained attention and tolerance for detail rather than inspiration. The kind of work that doesn't tend to produce famous names. I keep thinking about the specific texture of that labour, the smell of the darkroom chemicals, the weight of the glass plates, which were not small. The POSS plates were 14 by 17 inches, and glass is heavy. The particular silence of an observatory at night, which is a different silence from most silences, something about the combination of altitude and purpose and the specific acoustic deadness of domed buildings. Nobody in that building in 1950 was thinking about what their plates would reveal 70 years later. Why would they? The plates were records of a stable sky, made for current operational purposes, expected to remain accurate indefinitely, because the sky was expected to remain stable. The stability assumption was not unreasonable. For the vast majority of sources recorded on those plates, it has held completely. 600 million entries, and the overwhelming proportion of them still correspond to detectable objects at the recorded coordinates. The assumption was right for 99.999 something % of the catalogue. The fraction where it wasn't, that's where we are now. There's a specific thing that happened in the 1990s that made the VASCO comparison possible in a way it wouldn't have been earlier. The POSS plates were digitized. The original glass plates, sitting in the Palomar archive, physically intact, carrying 70-year-old emulsion records of the sky, were scanned at high resolution and converted into digital image files. The digitized sky survey, as it became known, made the data accessible in a form that could be computationally cross-referenced against modern digital sky surveys. Without that digitization, the comparison would require examining the original plates by eye alongside modern images. Possible for a small number of sources, not possible for 600 million. The digitization project was itself a piece of infrastructure work, unglamorous, slow, resource-intensive, done by people whose names don't appear in the VASCO papers. It made the science possible without being the science, which is maybe the most Naval Observatory thing about the whole chain of events. The discovery of vanished stars depended, at every stage, on careful institutional work done without any expectation of what it would eventually allow someone to find. The plates were made. The plates were stored. The plates were scanned, the scans were compared, and somewhere in that chain of patient, practical labour, the absences were waiting. Pan-STARRS sits on Haleakala, a dormant volcano on Maui, at about 3,000 metres above sea level. The air up there is thin and dry and mostly above the cloud layer that sits around the island's midsection like a belt. Good conditions for seeing. The telescope, actually 2 telescopes now, PS1 and PS2, though the survey data that matters most for the VASCO comparison came primarily from PS1, has a 1.8 metre primary mirror, which is not enormous by modern standards. What makes it unusual is the camera. 1.4 billion pixels, the largest digital camera ever built when it was commissioned, covering a field of view large enough to contain 36 full moons simultaneously. It was built to find things that move or change, asteroids, comets, supernovae, transient events of all kinds. The design philosophy was wide and fast rather than deep and narrow. Cover as much sky as possible repeatedly and look for differences between observations, which is, when you think about it, exactly the right instrument to eventually serve as the now half of a comparison with the then of the 1950 Palomar plates. Not because anyone designed it for that purpose, just because a telescope built to detect change, combined with a historical record of the sky before the change, produces the possibility of finding what changed. The comparison itself, the actual cross-referencing of 600 million sources, was not a single computation that ran overnight and produced a clean output in the morning. It was a pipeline, a sequence of processing steps, each one introducing its own methodological choices, each choice affecting what ended up in the output and what didn't. First, the coordinate systems had to be reconciled. The 1950 plates used one astrometric reference frame. Pan-STARRS uses another, more precise one, anchored to the positions of distant quasars rather than nearby stars. Converting between them accurately across the whole sky is not trivial. Stars move, not much, but measurably over 70 years, and that proper motion has to be accounted for, or a moving star looks like a disappearing star at its old position and a new star at its new position. Then the magnitude systems. The 1950 plates recorded light in the photographic blue and red bands that don't correspond precisely to any of the Pan-STARRS filter bands. Converting between them requires calibration, using stars present in both datasets to establish the relationship between the old magnitudes and the new ones. Sources near the detection limit of the old plates are the hardest to handle, because small calibration errors can push a faint real source below the matching threshold, making it look absent when it's just barely there. Then the source extraction, identifying which blobs of light in the digitized plate images correspond to real point sources versus plate defects, grain noise, diffraction spikes from bright nearby stars, edge effects. This is partly automated and partly requires human judgment on the ambiguous cases, and the ambiguous cases are, frustratingly, often the most interesting ones. After all of that, after the coordinate reconciliation and the magnitude calibration and the source extraction and the initial cross-matching, 150,000 discrepancies. Sources in the old data not matched in the new, or vice versa. And then the filtering. Checking each candidate against additional catalogues, looking for known variable stars, known asteroids, known artifacts, applying quality cuts based on the properties of the old plate image at each candidate position. The filtering is where most of the 150,000 went, quietly one by one into the resolved column. Known variable, plate artifact, proper motion mismatch, catalogue cross-match found, resolved, resolved, resolved. What remained after the filtering, around 100 candidates, had survived every check that could be automatically applied. Not confirmed as real, not confirmed as anything, just not resolved by the available tools. Those 100 then required targeted follow-up, individual observations with larger telescopes, multi-wavelength checks, manual examination of the original plates at the candidate positions. Some of those resolved during follow-up, quietly disappearing from the candidate list as additional data explained them. Some didn't. What I find myself thinking about, and I'm not sure this is a useful thought, it might just be a tangent, is the relationship between the instrument and the question it ends up answering. Pan-STARRS was not built to look for Vanish stars. The Palomar survey was not made to serve as a historical baseline for a future disappearance investigation. The digitization project was not undertaken because someone anticipated VASCO. Each piece of infrastructure was built for its own reasons, and the combination of them, decades later, produced a capability that none of them was designed to produce. The question found the tools, or the tools, accumulated slowly over 70 years of separate institutional decisions, eventually became sufficient to answer a question that nobody had quite formulated yet when any individual piece was being built. That happens in science more than the clean narratives suggest. The instrument comes first, sometimes. The question arrives later, when someone looks at what the instrument can do and realizes what it's now possible to ask. There is a surface around every black hole called the event horizon, and the name is more precise than it sounds. A horizon in the ordinary sense is the line beyond which you cannot see. Not because nothing exists past it, but because the geometry of the situation puts it outside your view. You move toward it, it recedes. You never actually arrive at it. It's defined by your position, not by anything inherent in the landscape. The event horizon of a black hole works similarly, except that it's not defined by your position. It's defined by the physics of space-time itself, and it doesn't recede. Cross it, and the geometry beyond it is structured so that every possible path forward leads inward. Not toward the center as a direction you choose, inward as the only direction that exists. Light emitted from inside the event horizon does not escape, not because it lacks the energy, because the space-time geometry past the horizon is curved so completely that outward doesn't exist as a direction anymore. The light travels forward in time, which is the only direction anything travels, and forward in time inside an event horizon means forward toward the singularity. The light never reaches the outside, not delayed, not weakened, just structurally prevented by the shape of space-time from arriving anywhere we could detect it. This is what makes a black hole formed by direct collapse different from almost any other object in the universe, in terms of what it communicates to the outside. A neutron star, dense as it is, still has a surface, still emits radiation, still interacts with infalling material in ways that produce detectable signals. A white dwarf glows for billions of years, cooling slowly, radiating the stored heat of its formation. Even objects we consider dark, cold molecular clouds, brown dwarfs below the fusion threshold, rogue planets drifting through interstellar space, interact with light that passes near them, bend it gravitationally, occasionally occult background sources in ways that reveal their presence. A black hole formed from total stellar collapse has none of that. The mass is there, gravity persists, the space-time curvature is real, and in principle a black hole can be detected through its gravitational influence on nearby matter or light. But a stellar mass black hole sitting alone in space, not accreting material from a companion, not located near enough to anything for its gravitational influence to be measured, that black hole is, for all practical observational purposes, invisible, not difficult to detect, not faint. Invisible in the specific sense that it produces no signal at any wavelength that any instrument we could pick up at stellar distances. The star was there. Now there is a region of space where the geometry is different, where mass is concentrated, where anything that falls in does not come back. And from here, from this distance, with these instruments, nothing. The sky at those coordinates looks the same as the sky around it. Empty. I've been trying to find the right way to hold this and I keep not quite getting there, which might mean there isn't a right way, or might mean I haven't found it yet. The information about what happened to that star, the specific sequence of events, the exact moment of collapse, the configuration of the core as it crossed its final threshold, that information still exists. In some physical sense. It's encoded in the state of the matter inside the event horizon. The universe didn't delete it. Deletion of information is something quantum mechanics resists at a fundamental level, and the resolution of that tension is one of the genuinely unsettled areas of theoretical physics, the black hole information paradox, which has occupied serious people for decades without a fully satisfying resolution. But the information exists somewhere inside the event horizon is not the same as the information is accessible. It isn't. Not to us. Not to any instrument at any distance. The event horizon is not a wall you could break through with a better telescope or a more sensitive detector. It's a feature of space-time geometry, and geometry doesn't yield to better instruments. Whatever the star did in its final half-second, the specific way its core collapsed, the precise configuration of mass and energy as the black hole formed, that record is inside, permanently, unreachably. This is the thing about these stars that sits heaviest when I let it. Not that they're gone. Things end. That's not unusual. What's unusual is the completeness of the ending. Most things that end leave something. A trace, a remnant, a signal travelling outward through the universe carrying information about what happened. These left nothing we can reach. The ending was total in a way that very few endings are. The mass remains, curved into the geometry of space, pulling weakly on everything nearby. But the star, the light it made, the information about how it lived and how it ended, is on the other side of a boundary that has no other side, not from here. Unreachable is a strange word for something that's still, in some sense, present. But it's the accurate one. The evening light does something specific to how I think about long projects. Sitting outside, watching the sky shift from blue to something darker at the edges, there's a pace to it. Unhurried, not quite slow, just moving at a rate that doesn't ask anything of you. I've been thinking about the VASCO collaboration in that light. Literally, I suppose right now, the park is getting quieter. Someone's dog ran past a few minutes ago, collar jingling, owner somewhere behind. The trees are doing that thing where they go very still just before the wind picks up again. VASCO, vanishing and appearing, sources during a century of observations, is a name that someone chose carefully, not a forced acronym, or maybe it was forced slightly, but whoever forced it understood what they were reaching for. Vasco da Gama, the navigator, the person who mapped coastlines that Europeans hadn't charted before. There's a quiet argument embedded in that name. We are mapping something. We are in the early part of the map, where the edges are uncertain and some regions are marked only with the notation that something interesting might be there. The collaboration started in any meaningful sense around 2017. Beatrice Villaroel, based at the Nordic Institute for Theoretical Physics in Stockholm, is the person whose name appears on most of the core papers, the driving researcher, the one who articulated the search methodology and assembled the team. The team itself came from a wide spread of institutions and specialties. Sweden, Spain, the United States, India, Ukraine, astronomers who study active galactic nuclei, stellar physicists, people who work on SETI, the search for extraterrestrial intelligence, who had their own reasons for caring about stars that produced anomalous transient signals. That breadth is interesting and worth pausing on. A collaboration that includes both stellar physicists and SETI researchers is not a typical configuration. The two fields have different priors, different methodological cultures, different tolerances for speculative interpretation. Stellar physicists tend to be conservative about invoking unusual mechanisms. SETI researchers, by the nature of their work, have to remain open to the possibility that some observations don't have natural explanations. Putting those two sensibilities in the same project creates a productive tension. The SETI researchers push to keep the anomalous candidates on the table rather than prematurely resolving them into mundane categories. The stellar physicists push back when the mundane explanations haven't been fully exhausted. The published papers reflect this. They're careful. They present the candidates, describe the ruling out process, note what remains unexplained, and explicitly include the non-natural hypothesis as one item on the list. Not the favoured item, but present, named, not dismissed. The search method at the core of VASCO is conceptually simple and operationally enormous, as covered earlier. Old catalogue against new catalogue, discrepancies flagged, candidates filtered. But there's a second strand to the work that gets less attention and is, in some ways, more methodologically interesting. The targeted follow-up observations. When a candidate survives the initial filtering, when a source is present in the old data, absent in the new data, and not explained by any of the automated checks, the next step is pointed observation. You take the coordinates of the candidate and you request time on a large telescope and you look at that specific patch of sky as carefully as current instrumentation allows. Optical, infrared, radio, X-ray, if the source characteristics warrant it. This is where the Gran Telescopio Canarias came in, the 10.4-metre telescope on La Palma in the Canary Islands, the largest single-aperture optical telescope in the world as of its commissioning. For the 9 simultaneous transient case from the 1950 plate, the team used GTC to examine the positions of each of the 9 sources at the deepest optical sensitivity currently achievable. They found at some positions faint objects that are not necessarily connected to the original transients, possible background galaxies, possible unrelated faint stars. At others, nothing. The follow-up work is ongoing. More candidates are being examined. New comparison surveys are being planned using more recent sky data, which would extend the comparison baseline and potentially identify sources that disappeared after the Pan-STAR survey began, adding a third epoch to the comparison, which would help enormously with ruling out artifacts and constraining the timing of disappearances. The sky is properly darkening now. The park lamps came on a few minutes ago, that orange sodium colour that makes everything look slightly warmer than it is. A couple walked past, talking quietly about something I didn't catch. The first stars are appearing, not many yet. The sky isn't dark enough, just the brightest ones, the ones that push through the remaining light. I looked up for a moment, the way you do. Habit, maybe, or something older than habit. The VASCO catalogue contains, at its current state, a set of coordinates where stars used to be. Some of those coordinates are in the sky visible from here tonight. Not identified ones, I don't have the catalogue memorised and the positions aren't labelled in any sky app I know of. But statistically, some fraction of the sky overhead right now contains locations where the old plates recorded something and the new surveys find nothing. The project continues because the question continues. The name holds. The map is still being drawn and the uncertain edges are still uncertain. And the researchers working on it are still doing what the name of the collaboration implies. Observing, comparing, noting what a century of looking has and hasn't found. It's fully evening now. The dog and its owner are long gone. The park is quiet in the specific way parks get quiet when the last light leaves. Not empty, just settled. The stars are coming out one by one into a sky that looks complete and isn't. Remember in chapter 10 when I was talking about Mira and the long period variables, I left something half finished. There was a possibility I mentioned, not stellar physics, not any natural process, and then stepped back from, said it needed more space and moved on. This is that space. The idea is Freeman Dyson's originally, or at least he's the one who formalized it in a way that stuck. Dyson was a physicist of unusually wide range, someone who moved between quantum field theory and nuclear engineering and speculative cosmology with a comfort that most researchers don't have or don't allow themselves. In 1960, he published a short paper in the journal Science, 2 pages. The paper proposed that any technological civilization, given enough time and sufficient energy demands, would eventually face a hard constraint: the energy output of its home star. A civilization that has spread across its home system, that is running complex processes at large scales, will eventually need more energy than its planet's surface can capture from its star. The solution Dyson proposed was structural. Build a shell around the star. Capture all of it, not necessarily a rigid shell. Dyson was careful about this, though the popular imagination fixed on the solid sphere version and never quite let go. What he actually described was a swarm, a dense collection of structures, habitats, collectors, whatever form the civilization's engineering took, surrounding the star at roughly the orbital distance of the habitable zone, capturing the stellar output comprehensively. The star would become, from the outside, invisible at optical wavelengths. All the energy it produced would be absorbed by the surrounding structures, used and re-radiated as waste heat at much lower temperatures, infrared mostly in the 200 to 300 Kelvin range. So a Dyson sphere or swarm or shell or whatever form it took would look from a distance like nothing at all at optical wavelengths, and like a faint, warm infrared source at longer wavelengths. A star that had been enclosed this way would disappear from the visible sky, just vanish from catalogues that operated at optical wavelengths, like say photographic plates from 1950 compared against a visible light survey from the 2000s. I want to be careful here because this is the part of the VASCO story where it's easiest to let the interesting possibility do more work than the evidence supports, and I've been trying throughout this to avoid that, and this chapter is the hardest place to maintain that discipline. The VASCO team has mentioned the Dyson sphere hypothesis in their published work. They have. It's not something I'm importing from outside their research. It appears explicitly in papers, as one item in the list of possible explanations for sources that vanish at optical wavelengths without leaving the expected traces of natural stellar endpoints. The reasoning is straightforward. If a natural disappearance leaves traces that we should be able to detect and aren't, and an artificial disappearance, a star being enclosed, would produce exactly the kind of clean optical absence we're seeing, then the artificial explanation deserves at least to be on the list. Being on the list is not the same as being supported by evidence. It's the same status as every other unconfirmed hypothesis in this investigation. What it does mean is that the researchers working on this consider it a legitimate scientific question, not a fringe idea they'd be embarrassed to associate with, but a hypothesis that the search methodology is actually sensitive to. If a Dyson structure exists somewhere in the VASCO candidate list, the way to find it is not through optical data. The star at optical wavelengths would simply be absent, which is what the candidates show. The signature would be in the infrared, a faint, warm, diffuse source at the candidate's coordinates, with a temperature and spectrum consistent with re-radiated stellar energy, rather than any natural warm object at that location. This is the search that has been done for some candidates. Carefully, the infrared data that was used to rule out the dust explanation, the same data, would also be sensitive to a Dyson structure's waste heat signature, at least in principle, at least for the closest candidates. Nothing has been found, no infrared excess at the candidate coordinates that matches the expected signature, which is, and this is my honest read on it for whatever that's worth, the expected result. The prior probability of any given candidate being an artificially enclosed star is extremely low. Ruling it out for current candidates doesn't close the hypothesis. It just means these particular sources so far don't show the infrared signature. What I find genuinely interesting about the Dyson hypothesis, not as an explanation for the VASCO candidate specifically, but as an idea, is what it implies about the relationship between energy and time. A civilization that has been expanding and developing for long enough will, if Dyson's logic holds, inevitably produce a detectable astronomical signature. Not a signal in the communications sense, not a message, not a beacon, just a consequence. A side effect of existing at sufficient scale. The waste heat of a civilization's operation radiating into the galaxy, visible in principle to anyone with an infrared telescope pointed at the right place. This is sometimes called a technosignature, an observable consequence of technology, as distinct from a deliberate signal. The idea has become central to a certain strand of SETI thinking, because it doesn't require a civilization to be trying to communicate. It just requires them to exist and use energy, which is what all civilizations do. Dyson published his 2-page paper in 1960 during a specific moment in the history of thinking about the universe. Post-Sputnik, pre-moon landing, a period when the technological possibilities of civilization felt newly limitless, and the question of what other civilizations might have achieved felt, to certain physicists, like a serious scientific question worth pursuing openly. The paper was written in that moment, and it carries that moment in it, the particular optimism and scale of ambition of mid-century physics. The idea has outlasted the moment. It's still being taken seriously 65 years later in papers published by researchers comparing photographic plates from 1950 to digital sky surveys from the 2010s and finding stars that aren't there anymore. Whether any of those stars were enclosed rather than collapsed, whether the absence is artificial rather than natural, is not something the current data can confirm or rule out completely. The infrared is quiet. That's the most that can be said. The concept Dyson offered in those 2 pages was not an answer. It was a shape, a way of thinking about what a sufficiently old civilization would inevitably become visible as, from a distance, to observers who knew what to look for. Whether anyone has become that, whether the sky contains any of those signatures, whether the VASCO candidates are connected to that question in any real way, all of that is open, genuinely open in the way that scientific questions are open when the evidence doesn't yet reach the hypothesis. The stars are gone, the reason isn't settled. And one item on the list of settled reasons is a 2-page paper from 1960 that has been impossible to completely put down ever since. Not everything in the VASCO candidate list stayed unexplained. Most of the 150,000 initial discrepancies resolved during filtering, but some candidates that survived the initial cuts Sources that looked at first pass like genuine absences were later explained by follow-up work, resolved eventually into something known. The resolution didn't happen all at once. It happened source by source over months and years of targeted observation and additional analysis, each resolved case quietly leaving the list and being replaced in the running tally of unexplained candidates by its own absence. This is worth spending time on, not because the resolved cases are the interesting ones. They're not, in the sense that makes this investigation significant, but because the fact of resolution matters for understanding what the unresolved cases actually represent. The most common resolution was variable star identification, a source present in the 1950 plates and absent in the pan-stars comparison turned out on closer examination to be a known variable star caught at an extreme minimum, a phase so dim that it fell below the detection threshold of the modern survey, or landed in a region of the pan-stars data where coverage was uneven. Cross-referencing against variable star catalogues flagged these. Some required additional observation to confirm, pointing a telescope at the coordinates during different phases of the suspected cycle and watching for the source to reappear. It reappeared. That's the resolution. Not dramatic, just. The source came back, on a schedule consistent with known variability mechanisms, and the discrepancy closed. Plate artifacts resolved similarly. A source in the old data that turned out on careful re-examination of the original plate scan to be a cosmic ray hit or a grain cluster in the emulsion, rather than a real astrophysical object. These are harder to identify than they sound. The digitized plate images have finite resolution, and the artifacts can closely resemble genuine faint point sources. In some cases, the original glass plate had to be physically re-examined with a microscope to distinguish artifact from source. When the re-examination showed artifact, the candidate was removed. Proper motion cases were perhaps the most conceptually interesting of the mundane resolutions. A star that has moved significantly between 1950 and the present, due to its own velocity through the galaxy relative to the Sun, would appear at slightly different coordinates in the two datasets. If the motion is large enough, the automated cross-matching fails to connect the old position to the new one, and the old position shows up as an apparent absence while the star is actually present, just not where the catalogue says it should be. High proper motion stars are generally known. They tend to be nearby since proper motion is more detectable at smaller distances, but some edge cases required verification. What the resolved candidates leave behind when you add them up is a cleaner remainder. Each resolved case functions as a kind of calibration. It tells you something about the methodology, about where it produces false positives and why, about how reliable the surviving candidates are likely to be. The resolved cases that came back as known variables establish that the methodology is sensitive enough to detect genuine variability at extreme phases. Good. That means the unresolved candidates, which don't show up even in targeted follow-up during every plausible phase of any known variability cycle, are genuinely not showing up, not hiding at minimum, actually absent. The resolved cases that turned out to be plate artifacts establish how the artifact signature differs from a real source. When surviving candidates are checked against those criteria and pass, when their morphology in the digitized plate image looks like a real point source rather than an artifact, that's meaningful, if not conclusive. I keep returning to the word conclusive and finding it unavailable. The resolved cases don't make the unresolved ones conclusive, they just make them more carefully bounded. More specifically unknown, if that phrase makes sense, which I think it does, just barely. The ones that came back were never the ones that were really gone. That sounds like it should mean something larger than it does. It doesn't, quite. It just means that a catalogue of genuine absences becomes more reliable, each time a false absence is identified and removed. The list shrinks toward the thing it was always trying to describe, sources that were there and then weren't and haven't been since. The ones that came back made the ones that didn't more visible. That's the whole contribution of the resolved cases. A clearing of the space around the actual question which remains exactly where it was. There is a version of this ending where everything resolves, where the investigation closes, the mechanism is confirmed, the candidates are explained, and the mystery folds neatly into the existing framework of stellar physics. That version exists as a possibility. It might even be the version that eventually happens years from now, when better data and better methods bring the VASCO candidates into focus. This is not that version, not yet. What we have at the current state of the investigation is a set of coordinates. 100-odd positions in the sky where something was present in 1950 and absent now, with no confirmed explanation for the absence. A smaller set, 9 positions from one April night, where sources appeared and vanished within half an hour, with no identified mechanism in the standard catalogue of astrophysical processes. A theoretical pathway, direct collapse, that could produce exactly the kind of traceless ending the candidates display, but has not been confirmed as the explanation for any specific source. A hypothesis, artificial enclosure Dyson's idea, that is almost certainly not the answer, but cannot be formally excluded by the current data. That's the inventory. It's not nothing. It's also not a conclusion. The thing about direct collapse, the thing I keep coming back to slowly, the way you come back to something you're not sure you've understood correctly, is what it implies about the universe's relationship to its own events. Most things that happen leave records. A star forms, and the surrounding gas cloud is disrupted, lit, pushed aside. A planet accretes and its gravitational influence shapes the orbits of everything nearby. A supernova occurs and the remnant expands for thousands of years, visible to instruments that didn't exist when the explosion happened. The universe is, in this sense, deeply archival. Its past is written into its present state in ways that careful observation can read backward, the way you can reconstruct a fire from the pattern of ash. Direct collapse breaks that. Not catastrophically, not in a way that undermines physics, but quietly and specifically. A star that collapses entirely into a black hole, without ejecting material, without producing a detectable remnant, without leaving any signal that escapes to the outside. That star removes itself from the archive. Not its mass, which persists as space-time curvature, but its history. The specific record of what it was and how it ended is sealed inside an event horizon and will not be retrieved. The universe performed an event and did not announce it, did not record it in any medium we can access. Just did it, in the dark without witness, and moved on. I find this genuinely difficult to sit with, and I'm not sure whether that difficulty is appropriate or just a failure of my intuition to extend properly to these scales. Because the universe has always been doing things without announcing them. Stars form and die in regions so dusty that optical telescopes can't see in, and we learn about them only through radio and infrared observations, and some we don't learn about at all. Events happen beyond our cosmological horizon, the boundary past which the universe's expansion has carried things faster than light can travel toward us, and those events are simply not available to us, not because they're hidden, but because the geometry of an expanding universe creates a limit. The universe is full of processes we can't observe. This is not new. What feels different about direct collapse is the proximity. These are not events beyond the cosmological horizon. They're stars that were close enough to be photographed on glass plates in 1950. They were in the observable sky. They were recorded, and then they ended in a way that produced nothing we can reach. The distance between was observable and ended undetectably is what makes it strange. Not philosophically strange, physically strange. A thing that was here in the accessible universe slipped into a state of permanent inaccessibility, still present in the mass sense, unreachable in every other. There's nothing more to conclude from this than what the evidence provides, which is less than the question deserves and more than nothing. The sky has gaps in it. Not visible gaps. The sky looks continuous, complete, full of light. But the catalogues have gaps. The comparisons have gaps. Specific positions where the record says something was, and the sky now says nothing is, and the explanation for that discrepancy is still being worked out by people with better tools and more patience than this narration has. Whatever ended at those coordinates, whether it collapsed silently into a black hole or dimmed below detectability through some mechanism not yet identified, or was enclosed by something we haven't confirmed exists, or was simply recorded incorrectly in 1950 and was never really there. The ending was quiet. No announcement, no remnant the universe saw fit to leave where we could find it. Just the old record and the new absence, and the space between them that research is slowly trying to close. The plate from 1950 is still in the archive. The stars on it are not all in the sky. That is where this started, and it is, more or less, where the understanding currently sits, not much further along than the fact itself, which is either humbling or clarifying depending on how you hold it. Both, maybe. If this is the kind of thing you find yourself wanting to keep thinking about, the quiet gaps in things, the physics that operates without witness, the universe's habit of performing its largest events in silence, there are other nights here, other topics, other long, slow walks through the stranger parts of what we know and don't know. If tonight helped with sleep, or with something else, that's enough. Sharing it with someone who might also be awake at the wrong hour, staring at a ceiling, looking for something to settle the mind, that's the kind of thing that keeps this going. The sky outside, wherever you are, has stars in it that are not in any catalogue, and stars in the catalogues that are no longer in the sky. Rest well.